Last class, what did we understood about the properties of semiconductor on the basis of conductivity and resistivity. So semiconductor conductivity is in the mid-range and its resistivity is also in right. So this is the first definition of semiconductors. And then we talked about that in most of the electronic devices, right? Because we have computers, we have these mobile phones, we have all those smartphones, and we have calculators and so many things. And then we have laptops and all the other electronic devices, right? So all those electronic devices heavily use these semiconductors, right? So why do we do that? Because in semiconductors we can control the current, right? How much current you will be want to have in some device, so that we can control by using the semiconductors. That is why many industrial material are used are based on this semiconductor device, right? So this was the thing, and then we also talked about that. We have these elemental semiconductors, right? Elemental means that it is made up of single elements. There are organic semiconductors and there are other mixed semiconductors as well. But yeah, in our class, we'll only talk about the elemental semiconductors, right? And then we talked about the energy bands. So energy bands were the closely spaced energy levels that we talked about in the atom. And then we had two kinds of band, conduction band and the valence band. So conduction bands are responsible for the currents in the semiconductors, and then they are they consist of free electrons, right? And then we have these bounded electrons in the valence band. And then we understood about these energy band gaps. So the difference between the lowest energy level of conduction band and highest energy level of the valence band. And the gap between them was called the energy gap, right? And on the basis of energy gap, then we defined different kinds of materials. Conductors' energy band gap was zero, as as Mariam said in the last class, pointed out. And we can also have the overlapped energy levels in conductors. And then we talked about semiconductors, so they have a particular band gap. So their band gap is less than 3 electron volts. So those are called the semiconductors. An example of them is silicon and germanium. Silicon had 1.1 electron volt band gap. Germanium had 0.7. And then we had insulators which had more than 3 electron volt energy band. So that was the definitions of conductor, insulator, semiconductor on the basis of energy band. And then we talked about holes. So what are the holes? When from the silicon lattice, the electrons leave that lattice point, so those create the holes, right? When the silicon removes or when the silicon electrons are removed due to some thermal rejection, right? So then those places are called holes and they have positive charge. So then we talked about the types of semiconductor. One was this intrinsic semiconductor. In intrinsic semiconductor, what was the property? So they are made up of single element. No impurities are there. And then we talked about the intrinsic semiconductor and the number density. The number density of the electrons and moles are same for the intrinsic semiconductor. So that we talked about in the last class. And we also saw that energy band gap was how much for this intrinsic semiconductor. And the energy band gap were quite high. That is why we use this extrinsic semiconductors. And then we talked about the kinds of semiconductor. One was n-type that we did in the last class, right? When we put or when the technical term is doping, right? So when we do pentavalent element,
So,
that is of they have doping. Yes, yes, Mariam. Hello, yes, Mariam, are you saying that?
so your voice is cracking.
My voice is correct. How is it now? How is it? Is it okay now?
A little, it's still cracking.
Right. Now they have fixed how is it now?
Yes, it's nice.
It's still, or is it still back?
No,
So
so
yeah,
it's better.
what we were discussing. N type, it's better. Okay, so we talked about N type semiconductor, right? When we put a pentavalent element, right? Pentavalent element has five of the electrons, right, in their outermost shell. So whenever all the electrons are shared, then it has one extra lone pair, right? One extra lone pair of electrons, one unbounded electron, and when it leaves its lattice site, then we have the extra. Yes, Assalam. Yeah, we have just revised because Mariam and Aisha were not there, so we are just recapping the right? So, yeah, so when we put pentavalent, so what is pentavalent? It has five electrons. The examples are phosphorus, arsenic, and and all these compounds like beta, right? Like this, right? Right. Right. Not them. So these kind of compounds uh, pentavalent compound, when we put them together, then it gives uh, when heavy conductor So I got disconnected. Is my voice clear? Right? Did you hear?
Sir, it's cracking a little.
Yes. Correct. Why? Now they have fixed it, right? We just changed and leaves its electron. So it will create a positive charge. It will not create a hole, it will create a positive charge. So we have free electrons due to donor element, and then we have due to thermally generated electron element. So then it will have the number density or the number of electrons would be greater than the number of holes. So whenever you see the number density is number of atoms or number of particles for electron, right? So whenever you see the number density of electron is higher, so that kind of material would be the N-type semiconductor, right? So these are the example of N-type semiconductor, and then to this N-type, it will create a donor level, right? These are the examples. And this we did in the last class. Now let us quickly talk about the P-type semiconductor. So N-type because we have number of electrons or the number density of electrons that is high. Now let us talk about P-type. What is the P-type? Type when try valid and that is called P-type semiconductor. And what are the example of the trivalent elements? So that is these are uh, these are the trivalent elements, right? And then we have let's say we have this lattice, right? Lattice is of silicon, and then we have so, all these electrons will be shared, right? All these electrons will be shared. Now, there is not any electron for aluminum, right? So what will happen that this one electron, right? One electron will leave its site, and let's say this electron leave its site and it is here, right? So let's say this electron leaves and it comes here. So it will create, right? It will create a hole in here, right? And this would be again a negative charge, right? So this would be a negative charge. So this will create a hole, and the other would be, let's say the thermally generated, let's say this electron also. This is thermally. So this electron leaves, and this electron is right. So this electron comes in here, and this is a hole, and then we have a hole again, and then we have this electron. So what would be more? What would be more? Holes would be more, or the uh, electrons would be? Which quantity would be? Yes, which quantity would be more?
Electrons.
You see that there is one hole created due to acceptor, right? One hole is created due to acceptor, and this will be negative charge, right? So this will become a negative charge, and one hole created due to this thermally generated electrons, right? So then there are two holes and only one electron. So what would be greater? What would be greater? So,
Holes.
number density, number density of uh, uh, is the other thing. And again, mechanisms are involved. Two mechanisms are involved. One is holes are created. Acceptor, acceptor element. In the previous case, electrons were created due to donor element, right? So there were extra electrons. So that those electrons were created due to the donor element. Now there are extra holes are created due to acceptor element. So this gap is provided by the intrinsic semiconductors, right? So it is creating a hole due to these acceptor elements. And then you have the holes, or I should write electron and hole pair created or by two mechanisms we are getting holes. So that is why the number density of holes is large, right? And then what it will do? So it will create an acceptor energy level here balance. Right, so you guys saw that due to the N-type conductor, N-type semiconductor, there was donor energy level, right? But due to P-type, there would be an acceptor energy level. So these are the key differences, right? So when we write the energy band diagram, so this would be there is the conduction band, and then we have the valence band. the EV, this is the DC. And above EV, we will have another band, and that is acceptor, right? These are the differences between the P type and N type. Is it clear to you all of you guys? Is it clear? When we do a trivalent compound, so trivalent compound has only three electrons in the outermost shell. So it can share only three electrons, right? So it has one empty space. So one electron can be put in there, right? And whenever we have n-type semiconductor, so that is pentavalent, so it has five electrons. So when four and silicon only can share four electrons, right? Then four electrons are shared and one electron is left. So that is why we have this n one electron which is extra. So that is why this is n type. In there we have one whole extra. So that is it is called p type. P means positive type semiconductor, right? So you guys please note it down, and then we'll talk about. So then we'll do numerous calculations, and then it will be very easier to understand. You guys please note it down. Whenever you guys want me to scroll down, please tell. Whenever you guys want me to scroll down, please. Then and again, the differences will be same for germanium and silicon. So what was that? For germanium, this difference was, or for silicon, this was 0.045, and for germanium, this would be 0.0. Right. So this difference would be same and as whatever was for the uh, donor and this conduction. In the case of N-type semiconductor, we had here this was the donor band, and then the difference was this. Similarly, for acceptor band, the difference would be the same. And it will become very clear when we will, whenever you guys have taken down. Yeah. Okay, so let us do some questions, and it will become very clear. But before we do that, let us write. So, in N-type semiconductor, number density of electrons that is greater than number density of air. N is number density. Right, means that number of electrons per unit volume. And similarly, NH is number density of holes, number density of holes, and that is NH, right? And then we have type type semiconductor number density of holes that is greater than number density of electrons. And there is one formula for intrinsic semiconductors. Number density of electrons that is equal to number density of holes, and this is called the number density of intrinsic. So N, and there is a formula which relates for N-type and P-type extrinsic semiconductors. So for extrinsic semiconductors, Ne and multiplied by NH, that would be Ni square. Whatever, let's say whatever that intrinsic semiconductor was, and then in that intrinsic semiconductor, if we put some impurity, then this relation should right. This is very, 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 very. This has to be understood, right? Let us do some question, and this will become very first. Let us for question. Right. So what is the question that we have? Suppose a pure silicon crystal has 5 into 10 to the power 28 atoms per meter cube. Right, so this is the number density of pure silicon crystal. It is cubed by, or it is grouped by, is grouped by 1 ppm. So we'll talk about what is ppm, concentration of pentavalent. Pentavalent arsenic. Its arsenic is pentavalent calculate number density of electrons and holes given number density of intrinsic semiconductor, that is 4.5 in 10 to the power 16 per meter. Right. So this is the thing which is given. And now we have to find out what is given. So number density of silicon, that is given. That is how much? That is 5 into 28, 10 to the power 28 atoms per meter cube. So that is the whole density of crystal. Right? This is the whole density of crystal. And then you are also given Ni. What is Ni? So in the intrinsic semiconductor, how much you have the equal amount of electrons and holes. Due to some thermal generation, how much is the electrons and how much is the holes. This is pure intrinsic without any doping. Without any doping, this amount is 4.5 into 10 to the power 6, 16 per. This is the intrinsic one. Now we have to calculate that what is the number of electrons in intrinsic one and what is the number of holes in the extrinsic. Right. So we know that if we are doping, if we are doping by pentavalent element, what kind of semiconductor would be that? What kind of semiconductor would be that? If we are doping a pentavalent element, if we are doping it with the pentavalent element, means that we are doping with five electron element, five valence electron element. So, which one would be higher, electron or holes? Yes. What kind of semiconductor would be there? We are doping with pentavalent. N-type, right? Because we have five electrons, four would be shared and one would be remaining, right? So one extra electron would be so
Yes,
that
sir.
that would amount to the N-type semiconductor. So this is the N-type semiconductor, right? N-type semiconductor, and which means that number density of electrons that would be larger than. Yeah. This is one. Now, we already have, so what is the doping, right? What is the doping? ppm means that we are doping, the definition of ppm is parts per, or this is particles per million, right? Generally called parts per million, so in this case, this is particles per billion, right? So for 1 million, right? For 1 million or for 1 million silicon atom, we have one arsenic element, right? So that is what it is saying. For this much amount of for this much amount of density, number density of silicon, what would be the number density of arsenic? So number density of arsenic, that would be how much? That would be 5 into 10 to the power 28 atoms per MQ divided by million. Right? Is it clear? Is it clear?
Yes,
Yeah.
sir.
Yeah, because for 1 million, for 1 million silicon, we have one arsenic. So for one silicon, we have 1 by 1 million arsenic. So for this much, whatever this quantity is, for 5 into 10 to the power 28, 1, this would be 5 into 28 into the power 28. So this will be number density of the atom, right? How much is it? What is the power of 3 million? What is the power? What is the power of 1 million? 1
10
lakh,
is
yeah, 10 is
6.
10 is to 6, right? Because 1 lakh is 10 to the power 5. 10 lakh is 1 million, so that will be 10 to the power 6. And atoms or we can use 5 into 6 power 28 minus 6, that is 20. And let's write per meter. This is the number density of arsenic, right? In that crystal of silicon. So every silicon atom, how many electrons it will contribute? Every silicon atom, how many electrons will it contribute?
2.
One arsenic will contribute two. One silicon atom will have one extra electron, right? Right? One arsenic electron,
Yes, sir.
right? One arsenic electron will have one extra electron. So it will create one. So this much amount of arsenic will contribute to this much amount of donor electron. So that would be how much? That would be 5 into 10 to the power 20 per liter, right? And then there would be thermally generated electrons. Number of electrons, total number density of electrons, that would be equal to number density of donor element plus number of electrons which is thermally generated. But this amount is pretty small as compared to this one, so we can write NP as similar, right? Because ND is really large amount. So this we can do, right? Where I should write where ND is donor electron and ND is thermally generated, right? So then we have got our number density of electron. That is how much? That is 5 into 10 to the power 50 per meter. So we have number density of electron. We have number density of intrinsic semiconductor. What was that? Was 4.5. So 4.5 into 10 to the power 60 per meter cube. So we can calculate the number density of holes using the relation what? Number density of electron, number density of holes, that is equal to Ni squared. So this number density of electron is 5 into 10 to the power 22 into NH, and Ni square is how much? 4.5 into 10 to the power 60 and 4.5 into 10 to the power 60. So NH is 4.5 and 10 to the power 6 point 5. Right, with that 0.5 and 10 to the power 50 divided by 5. This is 0.9. And this would be 40, right? 40, 4.05 and into 10 to the power 32 minus 10. That is 10 for 10. Number of holes, that would be 4.05 10 to the power 10 per meter. So as we predicted, that number of electrons would be larger than number of holes. That is the answer that we have. Right? Is it clear to all of you guys? Is it clear? Yes, is this question clear, guys?
Yes, sir.
Okay, you guys please note it down. Next question would be direct question. You guys can quickly get, like, yeah, whenever you guys want me to scroll down, please tell me. Yeah, whenever you guys want me to scroll down, please tell me.
Sir, can you please scroll down?
Questions are very simple and they can get you 3 marks or so, right? In the semiconductor type of questions, they will generally ask and the last chapter and one chapter is remaining, which is the fifth chapter, right? And I will check what are the topics that I have mixed. So I will put those topics that I have, right? Then on Yeah, whenever you guys have noted,
Done, sir.
then okay, now let us do other questions. Right? Everyone noted, right?
Yes.
Uh, so a semiconductor has one electron and the pair concentration of it now on doping, certain concentration of becomes becomes 4 into 10 to the power 10 or 2. Right. So then you have to find out. First question is that what kind of semiconductor it has become, and the second question is that what is number density of electron over right. So first question you guys can quickly tell, right? What kind of semiconductor it has become? What kind of semiconductor it has become?
N type.
What type? Hmm. So what is increasing, right? What is increasing? Which concentration is increasing? You see that initially
Holes.
holes are increasing. So what kind of semiconductor is it? P-type, right? Whenever you have holes greater than number of electrons, number density, that is P-type. Whenever you have number of electrons greater than the number of holes, that is N-type, right? So just remember the letter N that corresponds to negative, that corresponds to electron. Whenever you have N-type, that is related to electrons. Electrons are large, right? Whenever you have holes which are larger, so that will be type, right? So remember from N negative electron, N type electron, P type holes. This will become right. This will become so. This is a P type. Now the second question. So initially, what was the case? Initially, the number density of electron and number density of holes that is equal. So what kind of semiconductor is this?
N type.
Both are equal. So what kind of semiconductor is intrinsic? That is intrinsic semiconductor, right? Have I to guys about this? Yeah. Right. Intrinsic semiconductors, number of electrons, number of holes that. And you can check from this one also, right? You can check from this relation also that what is the relation, right? So if you have NeNH, that is the Ni square, and if Ne equal to NH, then you can write in place of NH, you can write Ne. So that is Ni square. So this is Ne square equals to Ni square. So Ni is Ne, that is NH. So for intrinsic semiconductor, number of holes that is equal to number of electrons, right? Because the holes are created due to the movement of electrons. So initially, these are equal, which means that this is intrinsic semiconductor. This value, which is given, this is actually Ni, right? So Ni that is given, that is 2 into 10 to the power 8 for cycle, and then NH you also have, right? After doping, NH is 4 into 10 to the power 10 meters cube, right? Then we can calculate using Ni and Ne. Ne H equals to Ni square. Ne is, we don't know, NH is 4 into 10 to the power 10, and Ni is 2 into 10 to the power 8, 2 into 10 to the power 8. So how much would be this? Ne into 10 to the power 8 or 16, and divided by 2. The, you see that the amount of number density of electron, concentration of electron is smaller than concentration of holes. So now you tell me, what kind of semiconductor is this? This is a p type, right? So from here we can also see that this is the p type. So please, you guys, if you guys have any doubts, please ask me. Otherwise, the problem, and then we will move on to the judge. Guys, please put it down, and I will be back in a minute. Right? Back. Yes, noted, guys. Should I scroll it? Noted. Done, everyone?
Yeah.
Done. Arsalan and Mariam. Arsalan, where are you?
Yes, sir, I'm done.
Done, done. Yeah. The next part is, so do you guys remember chapter uh, third chapter? And in third chapter, we saw the relation between current and drift velocity. So do you guys remember that? What is the relation between current and the drift velocity? Yes. Yeah. So do you guys remember that? Hmm. So the relation between the current and drift velocity was this one,
Yes, sir.
right? So this was the relation. And then we also learned that the resistivity or conductivity was reciprocal of resistivity, right? And
Yes,
then
sir.
we also learned about one thing more, which was mobility, right? So what was mobility? This was VD by D, right? This was mobility. And one more thing that we learned was what was this drift velocity? So this drift velocity was acceleration, right? Which was E by what was this M, right? And then tau. This was the drift velocity, right? Because if we remember, the force was E divided by M, so that is acceleration into T. That is it. Yes,
Sir, what does E stand for? The capital one.
this one. Oh, this was electric field, right? This was electric field.
Yes, sir.
So, yeah, this was the electric field, right? Yeah, so this was the drift velocity that we talked about. Okay, so then in this part, what is the current or what is the conductivity of semiconductor? So we know that there are two things involved, right? One is the electrons, free electrons, and then the other one is holes. So the current in a semiconductor will have two parts. One would be electrons and the other would be right. Similarly, the conductivity in the semiconductor. So conductivity in the semiconductor is defined as E and mu and Ne or N. So this is the conductivity in a semiconductor. And similarly, for if we write for electrons, the conductivity would be how much? That would be mu e and a number density of electrons. And for holes, I should write for electrons. For holes, the conductivity would be how much? So this would be H, and this is E mu H. So this mu is mobility, right? And then number density of mu E is the mobility of electrons. H is of holes, right? So the total conductivity of a semiconductor is also represented as and sigma E plus the sigma H. This is a very important information. This one is very important and this one also. So we will do one question based on this, right? So let us do that question and then you guys will let us do that question. Just find that question. And a semiconductor is have uh, an electron concentration of 8 into 10 to the power 30 per centimeter cube and whole concentration of 5 into 10 to the power 12 per center. Right. So the questions are, is the semiconductor N type or P type? And second question is that calculate resistivity of electrons and holes, right? If QE is 300 centimeter cube per volt second, and then this is how much? Mu H, that is 100 centimeter square per. So these are the information which are given, right? First question is that what kind of semiconductor is this? What kind of semiconductor is this one, right? What kind of semiconductor is this?
N type.
So number of electrons is larger, right? In the first question, number density of electrons that is greater than number density of holes. So which implies that this is N type semiconductor. Yes, correct. And then we have to find resistivity, right, of electrons and holes. So what we can do, right? We know that what is so we know that what is conductivity of electron. That is how much? Conductivity of electrons is how much? That is E, mu E and N. And conductivity of holes, that is how much? So that would be E and H and NH. Let us find both these out and then we can calculate the corresponding resistivity, right? This would be how much? Okay, so this is how much? Electron is 1.6 into 10 to the power minus 90 and mu A is 300. Now this is centimeter square, right? Centimeter square. This is centimeter into centimeter volt second. So that is SI unit, right? We have yeah, we can, so we don't have to bother about that. And then we have this NE. NE is how much? So NE is 8 into 10 to the power 30. 8 into 10 to the power 30 per centimeter, right? And then we will have right, that this will be this is centimeter, right? And this centimeter we can write it as this is 2300. This is 8 into 10 to the power 30. And this is how much? Centimeter is 1 by 100. 1 by 100 and then 1 by 100. And then we have this centimeter, so that is again 1 by 100 and 1 by 100, then 1 by. And then these centimeter will cancel each other out, and then we'll get 1 centimeter. This will be centimeter, this will be meter, meter volt per second. This is conductivity. So how much this divide? How much 1 by 100 cancel, and this 1.6 power 90 10 to the power minus 6, and then 300 8 1, and this is per meter volt second, right? This would be, this is 1.6 into 8 into 23, and this is 10 to the power 4, so this is going to be the power, right? And then what do we have? This is how much is this? 1.68. And remember that we have to be very careful with the, right, very careful with the units. What units we write? This is per meter volt per second, right? So this would be how much? This would be 0.94 and per meter volt per second. This is the conductivity of electrons. Similarly, we can also calculate the conductivity of holes, right? Conductivity of holes would be how much? 1.6 into 10 to the power minus 5. And then how much is this? I should have already written, but yeah, how much is that? H is 100 centimeters square per volt second, and then we have how much is it? 5.5 into 10 to the power 12. 5 into 10 to the power 12 divided by centimeter. I'm writing these because we have to write it in SI units, right? So this would be how much? Okay, this one is the right. So 1.6 and then into 5, and then this is minus 19, and then this is 12 plus 14. So this is 10 to the power minus 5. And then 100 will again come from here. that we have already seen. So this would be meter volt second. Be how much? This is 8 into 10 to the power minus 5 into 100. 8 into 10 to the power minus 3 per meter volt. This is the conductivity of. So resistivity of electrons, that would be 1 by sigma electron, and that would be how much? 1 by 0.94. This is how much? 1 divided. That is 0.34, right? And this would be volt to meter second. Right? But what is the unit of conductivity? Resistance is right rho L by A, and resistance is uh, resistance is volt per current, right? And this is rho L by A. This would be how much? Volt meter square, and then divided by this length meter, and then this current, right? So what should be the so unit should be what? Or we can write ohm meter, right? So we can write difference, right? So what is this thing? So conduct or resistivity of volts, that would be 1 by H. So 1 by H is 20 or minus, and ohm meter, that would be how much? 1 divided by 8 is 0.125, and this is how much? 1.5 into power. This is the so the holes will provide a more resistance to this current, right? Hole current will be less, and electron current would be large. So you guys please note it down, and if you guys have any doubts, please note it down. Is it clear, everyone? Is it clear?
Yeah.
Yeah. So please note it down, and let me in the while check the units, right? Okay. Whenever you guys want me to scroll down, please. And oh, so these parts, so you have also not it down. Yeah, whenever you guys want me to scroll down, please. That
Yes, yes, scroll down.
Then, yeah. And these questions are very important, right? Please practice them. And I should have changed the unit in here only. Otherwise, I would not have bothered about this one. But yeah, you guys can check or change the unit here also. Whatever way you see countable, guys, that I have changed the units in calculation itself. But from the starting point, you can also change. Let's say if I want to change this in per meter cube, so I can write this as 30 centimeter, centimeter, centimeter. So I can write it as 8 into 10 to the power 30, 1 by 100 meters, 1 by 100 meters, 1 by 100. This would be 8 into 10 to the power 13, and this 6 will go up to 90 and per meter cube. So we can do this initially also, right? This thing you guys can also, yeah, gives me some. Anyway, you guys want me to scroll down. So in the next class, this chapter will be over because we have to just write PN junction and then values.
Sir, can you please scroll down a little more?
Yeah, whenever you guys have put it down, first you guys.
Yes, sir, I'm done.
Then everyone put it. And guys, put it.
Yes, sir.
Okay, so we'll stop here and see you guys in the next class, right?